Let's look at this first example. We'll be doing this with the appendix from the textbook, something more like what you would be able to do, say, on an exam. I want to compare equipment cost and installed cost. For shell and tube exchanger, area is 100 square meters, so that's like the surface area on the outside of the tubes where the two fluids come into contact with each other, or temperature-wise they do. Using both carbon steel or stainless steel, pressure of 1 bar or 100 bar. And so to do this, what I'm going to need is to look through that appendix. So I have bits and pieces of this. So we start by calculating CP naught. And the equation for that is given in the appendix, equation A1, log base 10 of CP naught is K1 plus K2 times the log base 10 of the area in this case, plus K3 times the log base 10 of the area quantity squared. And then we're going to need to figure out what those K1s and K2s are. So we start browsing through the table and we're looking for a heat exchanger, in particular a shell and tube heat exchanger. And so you go through and finally we get to a page where there are heat exchangers. But if you read the list, shell and tube isn't in there. Okay, a lot of these are shell and tube. We need to make a choice. They were not specific, so you wouldn't be wrong if you used many of these. So you could have used fixed tube, U-tube. Yeah, those are probably the ones that would be most, bayonet. But probably the one that's most common is floating head. So in that case, K1 is 4.8306, K2 is negative 0.8509, and K3 is 0.3187. The A is going to be the surface area in meters squared, and this is valid for sizes between 10 meters squared and 1,000 meters squared. So at 100, we're good. All right, so that's going to allow me to calculate CP naught. I'm eventually going to also need to get some other things. There are all these graphs. I could have used those. We're going to need a pressure factor. So if it's a simple process vessel, this is what I would use. That's not what we have. Other process equipment uses this equation, which is very similar to what we were just using. And I then again have to find here my heat exchangers. So, okay, again we said that the floating head is the most common type, so we'll go with floating head. And notice that, okay, it depends on whether or not the pressure is at a particular value on the inside or the outside or both, okay? So if it's high pressure on both the shell and the tube, and for the purposes of this, they didn't tell us, so we'll go with that, okay? Then we'll use these equations at the top. If it is only inside the tube, we'll use these. Notice there isn't the option for high pressure in the shell and low pressure in the tube, because that would be a poor design choice for safety purposes, okay? All right, so now then, on choosing my values for C, I have the option of the pressure is less than 5 bar or between 5 and 140. So when we're talking about 1 bar, all my constants are 0, which means that the pressure factor is 1. And when I have the pressure at 100, it's going to be this set of constants. So we'll need to make a note of those. We also are going to need the materials factor. This is the crazy one where we have this ID number graph. So we have to find our heat exchanger here. And okay, so pretty much all of the types of heat exchangers are combined here, and it's a matter of whether it's carbon steel on the shell, the tube, carbon steel on the shell and something different on the tube, stainless steel on both. So we're going to go with carbon steel on both or stainless steel on both, because again the problem was poorly posed, right? So this is ID numbers 1 and 5, and I come back over here. ID number 1 reading across is FM equal to 1. 1, 2, 3, 4, 5. This one here, that one appears to be 2.7 is the material factor. Okay, so those are my material factors for my two options. All right, there now, my last thing is I need those B1 and B2 values. Okay, for heat exchangers, if we are going with, notice that all of the shell and tube type are lumped together here. 1.63 and 1.66 are my B1 and B2. All right, so that's the data that I needed to be able to solve this problem. So now we need to do the calculations. So I have already put those numbers into Excel, everything that we just looked up, okay? I've put in the area and the pressure. I know I'm going to need to calculate log base 10. To do that, it's log 10 of whatever that value is. Okay, and it is set up to use units of meters squared or pressure as in bar. Now I realize that numerically these are exactly the same, so it seems sort of silly to do that calculation twice, but that allows me to come in and change it later. Now then, CP naught, it is that equation that we had. Ooh. Let me pull up that slide. Nope, not quite there. No, okay, oh, I don't have it on the slide. Okay, bummer. That means I have to go back into this other file. This is a fun one to do, right? It's just equations everywhere. It's the very first page of Appendix A. All right, so log base 10 of CP naught is equal to this. So CP naught is 10 to that as a power. Okay. So coming into my Excel equals 10 to the power of, all right, K1 plus K2 times log of A plus K3, oh, I didn't mean to end that parenthesis, plus K3 times log of A squared. Now in that parenthesis, yeah. Okay, that's my C sub P naught, and F sub P is going to be equals 10, is the same form, but using the C's, plus C2 times log 10 of P plus C3 times log 10 of P squared. All right. So that's my CP naught and my F sub P. All right. Now then, okay, I've transferred all of those numbers here just for convenience. So F sub P for when the pressure is 1 bar is listed here, and when it's 100 bar, it's 1.38. FM when the materials are carbon steel is 1, and it's 2.7 when it's stainless steel. The C sub P naught is going to be the same for all of them because it's the same basic size of heat exchanger. Okay, so now we need the formulas for calculating C sub P, and those are back here. Okay, so C sub P is CP naught times FP times FM. That would be the amount it would cost to purchase it. We're going to have one little tricky detail we'll deal with at the end, but okay. So this is CP naught times FP times FM. Okay, that would be your purchase price for carbon steel. If I need it at a higher pressure, it's now, instead of 25,000, it's 35,000. If I want it in stainless steel at one pressure, it takes the price up to 68,000. And well, if I want it in carbon or in stainless steel at the high pressure, it's $95,000. So you can kind of get a sense of the impact of changing pressure and material. Okay, so now what about the bare module cost? Again, in our slides, if we multiply CP naught times B1 plus B2, that gets us CBM, the bare module cost at the reference state, 1 bar in carbon steel as the material. If I do it times B1 plus B2 times FPFM, that gets me the actual bare module cost. Now I'm going to go over it in a moment again. Let's do that calculation, but we'll talk about why we would do both in just a moment. So this times B1 plus B2 is my reference bare module cost. CP times B1 plus B2 times FP times FM. This is what would be the actual bare module cost. So this is the one that we would actually use for budgeting purposes. This is going to be important when we talk about the grassroots cost. It's a factor that I have to calculate in there. Now, in order to just drag and drop these, I need to use the F4 key and put in my dollar signs on those B1 and B2 values. Oh. Well, okay, it didn't do that well. F4, F4, return, and do the same thing on those, on the B1 and B2 values. Okay, so now I can take these and drag them down here. Okay, the bare module reference is going to be the same for all of them. That's what I wanted you to see. So that's going to be the same for all of them. But the bare module cost, this is to actually like truly get it installed as a fresh piece of equipment, ranges from $83,000 to $140,000, $420,000, $740,000 to install, as opposed to $83,000 to install. Okay, so that's a big difference there, and I wanted you to see that. Now, everything in those tables is done with I think it's $2006, 2001, I don't know, it was something. If we take this from this SEPSI was $397 for the table to today, where the SEPSI is $809, I redid those numbers there. So this is $1.5 million to install this stainless steel high pressure pump, $170,000 for the carbon steel low pressure pump. All right, so this is just a purchase in today's dollars. This is to get it fully installed in today's dollars. Okay, all right, so we'll take a short break and we'll come back and do the next example. All right, so for our next example, we're going to look at a centrifugal pump, 2.5 kilowatt, made it out of stainless steel, and it's operating at near ambient pressures. So for this one, we need our SEPSI value. So our current value is 809. We need the A attribute. So we're going to look that up in the appendix. We'll calculate CP naught. I'm going to do it two different ways this time. One using the tables. In an old version of the book that I have a hard copy of, it was pages 952 and 955. And then a graphical technique, which is page 959. We also will need FP, FM, B1, and B2, and that will allow us to calculate the bare module costs. So let's look at the appendix again. So again, we are looking for pumps this time. And as we scroll through this table here, hunting for the pumps. Oh, there they are at the bottom. Okay, so you need to know what type of pump you're using. So we have reciprocating, positive displacement, and centrifugal. I specified a centrifugal pump in this case, so these are our K values. The size attribute this time is shaft power in kilowatts. So that was given to us, so that's great, and this is valid for the power to be between 1 and 300, so we're in good shape. My other choice is to use these graphs, and I always moan when someone tells me I have to do a graph, but you know, those equations, especially on an exam, are not really all that much fun either. So on these, I don't actually have the picture for the centrifugal pump, but there's something like this. And what you're going to do is you're going to find down here your power, okay, you know, like 75 kilowatts or whatever, and come up and find centrifugal pump's curve, read straight across, and then this is going to tell you the value of CP naught, okay, in $2001, right? So we'll do it both ways. Pressure factor, again, this is for just a vessel, just a container. And for all the other process equipment, I use the equation and finding pumps on here. Okay, again, I have whether it's pressure less than 10 or between 10 and 100. We are in the pressure less than 10, so all of those are 0, meaning the pressure factor is 1. And then for my material, it was stainless steel, so I have to find pumps. I have to find the type, centrifugal, and stainless steel, and so it's ID number 39. Come back over here to this, and 39, and F is, it looks like it's about 2.5, okay? So that's all the information we need. Now we just need to do the calculation. So 2.5 kilowatt stainless steel. I called it 2 atmospheres just because, okay, near ambient, less than 10. The old value of SEPSI was 397. The current value is 809. These are the K values. These are the C values and my FM. Okay. Oh, and B1 and B2. I didn't look those up with you, but all right. So I did this using the table from the appendix. So I just calculated 10 to the K1 plus K2 log 10 plus K3 log 10 squared. Okay. Or I used the graph. Now in this case, the graph, the axis, what I find is CP naught divided by the power. Okay, so that was 1100 multiplied by the power of 2.5, and so CP naught is 2750. That's really not that different, right? And we're only going to take 2 sig figs. So your choice of which to do. The graphs aren't that bad if you're only doing like one calculation. FP is equal to 1, and I calculated then this using B1 plus B2 times FP times FM, and came up with $13,400, but that was in 2001 dollars, and so converting it to today's dollars is 27,331. Okay, only keep 2 digits. 27,000 is our answer. Okay. So we're going to go ahead and look at the distillation problem. I'm going to pretty much just leave you with the spreadsheet and very quickly talk through this, but what I want you to see is that a distillation tower is a lot more work. So a distillation column has a tower and it's got its internals. So in this case it's sieve trays, okay? It's going to have a reboiler and it's going to have a condenser. It may have to have a pump also. Depends on exactly how you have constructed this thing, okay? The reboiler is typically a kettle reboiler, although they could be a shell and tube. The condenser is quite frequently a shell and tube. The kettle reboiler is 23 square meters and the shell and tube condenser is 138 square meters. Okay, this is the information about that tray that we get from the spec sheet in the Appendix B that they give for the equipment. So let's look at what it takes to calculate this one. And again, I'm not going to go through every detail of it, but I have to do this for the tower, okay, which is just a tall vertical vessel. I have to do this for the sieve trays. Now on sieve trays, you're going to find that there's not going to be a pressure factor because they are totally internal. And so it really doesn't matter if they're at high pressure or low pressure because the pressure on all sides is going to be the same. So therefore it really doesn't matter high or low pressure. I did not convert these over to today's dollars. That's easy enough to do. I did the reboiler. And I did the condenser. Okay. So, and again, sometimes you also would need a pump. That's not an uncommon thing to do. All right, when you get all of this done, the C sub P for each of these things, okay, the CP naught, just to buy the thing, not get it shipped or anything like that. C bare module, so that I can actually get it installed. Just the tower itself, $500,000 in 2001, almost $1 million today. That's just the tower. Add in those sieve trays, $354,000 additional dollars. The reboiler, $380,000, and the condenser, $380,000. And so the total price for this fairly small distillation tower is $2 million. Okay? That's not taking into account utilities, which will be coming up in our next chapter that we'll be looking at. So we're going to take another break, and I'm going to come back, and if you'll download a copy of Capcost, and let's play with that next. Okay, so this is what Capcost should look like. If there's stuff in there already, then hit this remove all equipment button, and it'll take a moment, but it'll go through and delete everything that we've done. So the first thing that I'm going to recommend you do is change the value here. This is where you want to type in the current value for subsea. So for this year we're using 809 as the price, the chemical engineering cost index. Okay, then what we're going to do is we're going to hit add equipment. So the first example that we did was a heat exchanger. So click this and scroll down and find heat exchangers. Say next, and you have to figure out what type. Now it is the same options as are in that table. So we were doing this based on a floating head, shell and tube floating head. And we did this for carbon steel, with a maximum operating pressure of, and you can do either the 1 or the 100 case. I'll do the 100, and I'm going to do it on both sides. And my heat transfer area was 100. Okay. They didn't give us any information about number of shells, so we'll assume it's just 1. And then we're going to say finish. Okay. Takes just a moment, but it's going in and running Visual Basic code, and it has named it exchanger EO1, floating head at 100 bar, carbon steel, 100 square foot. The purchased equipment cost is $71,000, and oh dear, okay. There we go. The bare module cost is $170,000. Okay. I can edit equipment. I don't usually do this. In fact, if you do this and say I want to edit it, then just go in and change the part that you wanted to change. So like stainless steel. I'm not changing any of the rest of it. And it redid the calculations, except for it didn't. Cool. Okay. Yeah, sometimes that doesn't really work. All it did was it changed the label here. It didn't change any of my numbers. We'll have to go through and redo that and add new equipment if we wanted to. Now, I think that if I go through and just remove that one piece, I can, but let's just remove that piece. If we wanted to add something else, let's do our pump problem. Pump, next. Okay, it was a centrifugal pump. We made it out of carbon steel. Notice that cast iron is its first choice there. It's a very common type of pump, and it is typically cheaper than using carbon steel to do a cast iron pump. And let's see, that one was a 2.5 kilowatt pump. Okay, notice that it does give you options of changing the units, and it will deal with that, and we'll say that it was at 2 bar, and I am not going to have a spare. We've talked a little bit in class already about this, but it's very common that you have an installed spare. No spare is 0, okay? So it's very common that you're going to add a spare at the time, and so you just go ahead and purchase 2, but you only install 1. And so that's why you would like to go ahead and do that here instead of, you know, taking the multiplier on all of the installation costs also. And so finish. And it has done my calculations for me. I can add, okay, so let's add my tower. This is a tricky one. All right, so let's say, I don't even remember what I was making. It was stainless steel. Okay, the maximum, yeah, weld efficiency, you can change those, and that would be based on codes for the type of material that you're working with. Okay, if you are adding a demister, you would need to click on that here. This would be important if you have, say, liquids that might be entrained in the gas that's leaving the top of your tower, and you wanted to make sure that they did not. You would put a demister in there, but they didn't say anything about that, so we'll skip that option. And then trays. Are you doing trays or are you doing packing? Okay, we are doing trays. We are doing sieve trays, and we had 31 of them. They were made of stainless steel. The diameter of the vessel was given as 0.6096 meters. The height of the vessel, they said 19 meters. Oh no, the diameter was 2.5. That was the tray spacing I just put in there. Boy, okay. And the maximum pressure was pretty low in this. Oh no, 200 kilopascals Oh dear, 200 kilopascal. Oh, it has that. Okay. All right. And all the rest of this I'm going to ignore, do finish, and it's going to come up with my costs. Okay. So it did all of that. This is going to be a lot more efficient, right? Especially on things like towers where you've got a lot of them, or on a pump where you might want to have that installed spare, which means you're going to add the purchase price of one additional pump. Now we will in future weeks be looking at all of these other tabs, but for today we're only going to deal with the very front tab. Okay, the equipment cost data is on this last tab here, so if you wanted to update the numbers, maybe you had better information, you could come in here and change the K values, but also this is a place where you can look those up. Okay, and so just kind of, feel free to browse it. Just make sure that you always have access to a fresh, clean one of these. It's going to be easier to start from scratch than it is going to be to edit, is what I have always found. So that concludes this lesson. When we come back to class next week, we're going to be starting to look at reactors and what we need to do to design those. All right, see you in class.